time series. So we spend millions of dollars to get time series of ocean transport or other type of time series, and then we analyze them with the wrong tools. And one of the wrong tools to look at periodicity, we are obsessed with periodicity in time series in geophysical field timing. So we always look for peak in a spectrum. And a lot of people use, I don't know why, bias preserving spectra, and it is the worst idea that you can do. And I remember several years ago, I talked to Adam about it, and I was just like, Adam, like, these people are using something called the variance preserving spectrum. Like, what is this about? And he looked back at me and he's like, I have no idea why people do such a thing. Okay. So just as a note, we just talked about spectra. Variance preserving spectra seems to be an invention of oceanographers, and it's the worst thing we can do. Okay. All right. So today I'll be talking about some concrete examples, some case studies. So having listened yesterday to Amy and Mikhail, I'm kind of like doubting everything that I've done in the past, but here you go. So let's talk about these examples. So one of the things that I want to talk about and I've been involved with is a global drifter program in the derivation of some products for this program. So through fundings throughout the years provided by NOAA, NSF, as well as the Cooperative Institute for Marine and Atmospheric Studies here between UN and NOAA, AONL across the street. Okay. So the goal for this lecture, for my talk today, is to go over 3 case studies of uncertainty derivations and utilizations. Okay, so these are the things that I want to cover. Because you can think about uncertainty, but sometimes you want to use them, someone you want to derive them for your product, etc., etc. And so all the details of what I've been talking about today are in 2 papers. One in 2016 that I led, and one in 2022 that I led as well. And I've written the list of long collaborators, and you can see that Adam is in both of them, and so we spent a lot of time talking to each other about these topics. So I'll be covering a couple of examples from this paper and one example from this second paper. So if you want to look for more details, please ask me or have a look at these papers. So first example, characterizing errors and using uncertainty estimates. So I'm trying to make the distinctions here. I'm going to show you an example where I actually know, or I think what I know the errors are, and I'm going to characterize them. And then I'm going to use that characterization to derive down the line an uncertainty on a further estimate arising from the data for which I derive a characterization of the errors. Okay. So that paper, the goal was to take the position as a function of time of the drifters of the global drifter program and to produce a time series of drifter positions and velocities, estimates of these quantities, along with the uncertainty estimates at regular hourly intervals. But the obstacle to that goal was that the observations were uneven in time, and then we can clearly characterize them as being uncertain. So in this plot here on the left, you can imagine that we need a black line with a small black dot is the truth, and the observations, which are given by the colored squares, are actually the colored square, right? So it's uneven in time and it's very noisy. So how do you go, or how do you understand the relationship between the truth in black and the observations squares? Maybe I should move this down a little bit. It's too close to me. All right, so for Amy's sake and for others, of course, I have to give you a little introduction about the overall program. This is a snapshot of the status of the array as of a couple of days ago. So this program is funded by the U.S. National OceanUQ Administration, or NOAA, and this program maintains with international partners a global array of satellite track drifters to meet the needs of an accurate and global dense set of in-situ observations of near-surface currents, sea-surface temperature, as well as sea level pressure. And so it's interesting because, like the accurate word is in the definition of the program, whatever that means. And so a dense set, meaning that if you take the ocean and you divide it in 5 by 5 degree boxes, you get a number which is 1,250. Hence, this is a number of drifters that is intending to be in the ocean at any time. And you have 1,150 at the time, 1,250. So as of right now, they're a bit underperforming. And so our relevance for this first part is that here you have a cartoon version of a drifter, and the main thing is that at the surface you have a buoy that is located in space as a function of time, not by GPS. It is now, but it used to be located by the Argos system, not to be confused with the Argo program, but the Argos system. So the Argos system is basically, it works in, in a nutshell, the buoy is emitting a signal at all times, independently of the satellites around. There's a constellation of Argos satellites, up to 5 or 6, that are like orbiting around the Earth, and they are listening for these emitters. And when they hear the signal, they use the Doppler shift principle to locate them in space. Okay? So that's how it works. And this is the reason why the data that you get out of it is uneven in time, as well as quite inaccurate. It's very different from the GPS system, which you have on your phone, which consists of not an emitter on your phone, but you have actually a receiver that looks for GPS satellites, and then listen for the signal from the GPS satellites, do the processing on board, and then that data, that localization data, eventually can be transmitted to, let's say an Iridium satellite that is going to communicate the data. This is what is happening right now with the Global Picture Program. And it's a little bit more accurate. Before, we were relying on the Argos system. Okay? So hopefully you understand the distinction here and the reason why we had to deal with this problem. And so another introduction about the Global Picture Program. So for example, taking questions. So right now, currently in the array, there's one Argos drifter left. Okay? And the rest is Iridium. So even to this day, you still have some Argos. Like this. Yeah. So what drifters are solved, right? So what are we trying to do? All right. So we want to take the observations, and we want to, I'm not going to dwell into too much of the details. I want to focus on the derivation of the uncertainties. But what we decided to do is that we want to fit a model to the observations, and we want to fit a model within a sliding window to obtain estimates of longitude and latitude at R'ly interval. So let's say here the x-axis represents time. The y-axis with the x variable could be longitude or latitude, and we had those observations uneven in time. So that curve shape is supposed to represent a window over which we're going to consider the data with a given bandwidth. And as an example, within the data points that are within this window, we're going to fit a linear model that is simply a straight line, but is going to be some sort of fit over the observation, right? Classically, we have some observations, we have a model for the process, and we're trying to fit a model to the observations. So that's what we decided to do to obtain an estimate of the longitude or the latitude at some interpolation time, which is distinct from the observation times, okay? So for the product that we derived, we decided, at every top of the hour UTC, we're going to give you an estimate of the position and the velocity. So we need to get an estimate of that, of these quantities at a time where we do not necessarily have an observation. All right. So we just decided to do that. So we choose a mathematical model for phi and theta, longitude and latitude, and we simply said that they were a linear function, a polynomial of order 1 of time. So time is describing the time within the window where you're going to select the observations. And T naught is basically the interpolation time, or the time at which you want to get your speed. All right? So you have a polynomial both for the longitude and for the latitude. So if you look at this, you basically have 4 parameters that you're trying to estimate, right? At each interpolation time. So you can put them in a vector, and then you have this vector beta of all the parameters that you want to estimate. And it's kind of convenient to do this in terms of like displacement as a function of time, because if you so once you get your parameters, you evaluate this expression at time t equals t naught, and then your beta 0 parameter is the position that you're looking for. But actually, the beta one is the speed in the longitude or latitude direction. So by using such a model, you estimate at the same time the position and the velocity. Okay. So we decided to do that. So the way we decided to do that, and Elipot touched on that yesterday, is that we're going to look for a set of parameters. We're going to maximize a weighted probability of the observed data or weighted likelihood. So mathematically, the way it looks, it's a product of the probability of getting the observation that we observe given the truth, right? So we have this probability function, which is a function of these 4 parameters, all right? The observations as well as the truth, right? So the truth model that is here. So this probability P, right, is the PDF describing whether a location observation, the data, will yield the true location. So if you think about it, you can think of this probability as being the difference between the observation and the truth. That's the error. If you decide to define the error as being the difference between the observation and the truth, right? I see Amy cringing in the back, but no, okay. So that's basically the PDF of the error. Oh, great. So we have this mathematical expression, and but what is a P function? Like, what is it? Okay. So, well, we don't know what the errors are, because if we knew what the errors were, we would just correct the data, and then that would be the end of the story, right? So we need to figure out what the errors are. So let's go to the observation, to that example that I was giving you earlier. All right, so great. So now we're going to define the error. And how we're going to do that is that, well, it just happened that we had a subset of the drifters. We had 82 drifters that had both GPS and Argos positioning system. So we are very lucky because we actually look at the GPS data, right? And this is where we have to make some assumptions. We're going to say, well, we know the GPS are very accurate compared to the Argos. So we're going to do a little bit of tweaking to the GPS data, but we're going to say the GPS is the truth. And then we're going to compare to the same observation taken at the same time by the Argos system. So now we can work because we actually can calculate actually what the errors are in the data set by assuming that the GPS was the truth. So you can define the error in longitude and you can define the error in latitude with those delta phi and delta theta here. Okay. So, however, we had this information only for a little subset of the data of the drifters, like 82 of them. But the global drifter program right now has up to 25,000 drifters, right? So we don't know about the others. So Argos, for good or bad reason, is actually giving you not a standard error on the Argos location when you get data from Argos. It gives you a class, an error class. So you're going to get some Argos data, and they're going to tell you it's class 3, meaning that you have some sort of one standard deviation of the error, or the standard error, to be less than 250 meters. Class 2, it's between 250 and 500. Class 1 is between 500 and 1500. And class 0 has a standard error larger than 1500 meters. So that's useful, but that's not really useful when you're trying to put this in a maximum likelihood function, which I derived to you earlier, right? So having a class with a range of uncertainty, or an uncertainty that corresponds to a range, doesn't really help you to describe that probability distribution function, that analytical function that you want to put in your equation, and then that you want to maximize to get your best estimate. Okay? So what we could do is that, well, then we use that set of 82 drifters. We had actually quite a lot of data. I forgot, maybe we had 100,000 data points over the length of the lifespan of these drifters. And then what I've shown here, they were in the North Atlantic during the SPURS experiment, the first NASA SPURS experiment. And so we went ahead. And so here on the right, I'm showing you the PDF of the error in longitude or in latitude. So the jagged thin line corresponds to the empirical PDF, like it's a histogram, basically. Note that the histogram or the count of the PDF is shown on a log scale here. And so we did that for class 1, class 2, class 3, as well as all class together. Okay? And what we did is that we looked at, okay, so is the PDF of these errors well described by a normal PDF or a Gaussian PDF, right? So that would be the dashed line here. So you can see that in all the cases, right, the Gaussian PDF is not a good fit because it doesn't capture the tails of these distributions, right? So we decided, well, maybe we need to go a bit further. So we looked at another family of probability distribution function called the T-location scale PDF. And the student T PDF that you may have heard before in your statistics classes is part of that family of PDF. So we did that, and then we did a number of things to show that the T-location scale PDF was actually better than the normal PDF. And it has some consequences that I'm going to talk about in a little bit. But you can see that in general, like the classes of errors given by Argos, kind of made sense, right? So class 3 was supposed to be the one with the highest accuracy, if I can say so, and you can see that the distribution is narrower than the class 1 distribution of errors. And then here on the right, you can calculate the difference in longitude, which is a sign quantity. You can put the difference in latitude, which is a sign quantity, or you can look at the angular separation on a sphere, which is a positive quantity. Then we just for the sake of it, we fitted some exponential PDF to that distribution. So they actually have a much better idea than just the class. They're actually looking at the variance ellipse in 2 dimensions, and the R parameter that they give is the square root of the product of the major and minor axis of a ellipse variance on the position. But by prescription, that's not what UML is getting. Right? They're not getting those elliptical parameters. They're just getting that class, that one number. And that's not something I control. So obviously, if we use the oceanography as an example, we put it on top of the moorings. And then when we release a mooring, and then when the top of the mooring reaches the surface, typically we use Argos beacon to know where the Argos your mooring is when you do that. If you're not actually sitting in front of it, if you miscalculated the position of your mooring when you release it, then you're gonna wait for the Argos beacon. So the crazy thing is that it takes 114 minutes for an Argos satellite to go around the Earth. That may be the amount of time you may have to wait to get an Argos signal to know where your mooring is sometimes, right? And then they send you an email. So you have to have email on both. And then, you might wait up to 140 minutes to get one location. So I guess we use this instead of GPS because putting a GPS, submerge it, having to go back up, use Iridium for communications. Argos is, I think, a cheaper solution. Yes, all right. So as I said, it doesn't look like a normal PDF whose analytical expression is given here. And we think it looks more like a T-location scale PDF, which analytical expression is given here. So these two PDF have a lot of things in common. They are both centered around a location parameter. They are symmetric around the location parameter, which for the normal PDF is typically called the mean. Okay? And they decay away from the center at a rate that is given by the scale parameter sigma, which is called the standard deviation in the case of the normal PDF. And then the T-location scale PDF has an extra parameter, mu, given here, which basically changes the shape from the normal PDF. And it accounts for fatter tails and narrower peaks of compared to a normal PDF, right? And so it has a scientific expression. Gamma is just this mathematical expression. And so basically, the reason why I put this thing, which is funny to me, is that what is very important here is actually the presence of these outliers, the presence of the tails. Okay? So why is that? The reason why it's important, the presence of these tails, is that the estimation problem that I showed you earlier, where I bothered to put a likelihood function, and I was telling you that determining the position and the velocity means that you are trying to maximize this likelihood function. If it happens that your error are distributed like normal PDF, the problem simplifies a lot. And you can reduce it to a simple least square estimation, which is relatively common. And if you can put your equations in a linear system, then you can solve a least square problem. However, if your errors are actually not normally distributed, the least square method is going to put too much emphasis, or it's going to weight too much the tails of the distribution. So what happens is that the average locations have a lot of outliers compared to a normal distribution. And then if you do a least square to estimate the position and the velocity, you're basically going to put too much emphasis on this data. So we realized that it was better to get better estimates, in some sense, to actually use these characterizations, the T-location scale characterization. Okay? Without dwelling too much on the detail. So as I said, we fitted distribution to the observed errors. Another way of convince ourselves also that the T-location scale PDF was better than a normal PDF was to look at quantile plots, where basically we were comparing the quantiles of the observed PDF to the quantiles that would be given by a normal PDF or T-location scale PDF. And the take-home message here is that the red line, which is the T-location scale PDF quantile comparison in that Q2 plot, is closer to the 1-1 line. So this afternoon, for our activities, we're going to ask you to have a look at this type of diagnostics, hopefully. And so the fact that the red line was more aligned with the 1-1 line, the slope 1 line, was telling us that the T-location scale was better. Another thing that we were able to do is that we were able to look at the 2D histogram of the longitude error versus the latitude error, right, for each of the clouds. So by looking at this 2D histogram, you can see that this cloud, this density of observations, was basically a circle, meaning that there was no apparent dependency on the longitude error based on the latitude error, and vice versa. So we concluded, without actually doing too much statistical tests, that the errors in latitude and longitude were independent. So, because they were independent, we could do a couple of things. We could say that the joint probability of the errors between longitude and latitude was actually the product of the two marginal probability of the errors for the longitude and the latitude. So the reason that we could turn this one expression, this one PDF, into the product of two PDF helps a lot, because then we can substitute that into our likelihood equations, right? So we are like slowly building what that likelihood function is, because we want to optimize it, we want to maximize it, so we need to know what it is. So it turns out that you actually take the log of that likelihood function, and it's called the log likelihood function, which is typically the quantity that, in a computer you're going to optimize or going to maximize. Okay. So we're going to use the independence, build the likelihood, and then we are going to say, okay, they are distributed like a T-location scale PDF. And we actually fitted the parameters of this T-location PDF. So we have numerical values. And then we can put in the analytical expression. And now your log likelihood looks like this. Okay? So we actually found the negative log likelihood. And so now what we are going to try to do is that at every interpolation time, we are going to maximize or minimize, I forgot which direction we're going, this expression. So in this complicated mathematical expression, you can actually ignore the first line, because this is actually a constant number. But then if you look at this two lines, you'll see that you have a component here where your model, the model of the linear model of the longitude and the latitude are appearing with the parameters that we are trying to estimate. So here, this is not a type of expression that you can put into a linear system of equations, so you cannot use least square, and you have to rely on a non-linear minimizing algorithm. And this is what we did. But nevertheless, your algorithm spits out the parameters that are going to maximize or minimize your log likelihood function. So then, at every interpolation time, we can use those fitted parameters, evaluate it for t equals 0, that gives you the position, and then we could take the beta 1 parameters and that give you the speed. And that's the end of it. So, to wrap it up, to conclude, here's the interpolation method, if you want, the estimation method to get the position and the velocity. But we could get an answer, or we could get to these results only because we were able to characterize what the distribution of the errors were. So we used we describe the errors. We spent all that time describing the PDF of these errors, and that description was actually used to estimate, ultimately, eventually, the position and the velocity. So we basically weighted based on the temporal distance from the interpolation time. So now we get the position and the velocity. Great. And as I said, I forgot the numbers because we switched to GPS, but maybe it was like 12,000 drifters that we had to process at different lengths. And then it ended up being like 120 million estimates, right? So we had to do this nonlinear optimization 120 million times. Okay, great. But so how do you get uncertainty estimates associated with your estimates based on the method that we used? So this is what we did next. This is the second example I want to talk to you about. So we choose n equals 4 as your answer. I think that's what the question you asked. So what we used is that from the interpolation time, top of the hour, we chose to use 2 points before and 2 points after, right? So this is basically a variable bandwidth that we decided to use because, the temporal span between the interpolation time and the observation can change, right? So we basically use an adaptive window length, but we use the window that always encompasses 4 data points. Okay? I forgot exactly how we chose 4, but we did. So you obtain your estimates. So we put a hat on it, right? The beta hat. How do you get the variance of that beta hat? So the variance of your estimate, you take the square root of it. That's the standard error of your estimate, which is one way of quantifying the uncertainty. So how do you get that? So some theory, statistical theory, asymptotic theory, meaning that when the number of n points goes to infinity, is telling us that the difference between your estimate and the truth is distributed like a normal PDF, zero-centered, with a standard deviation that you can deduce from the second derivative of the log likelihood. Okay. That's what theory is telling us. The log likelihood that we showed you was very complicated mathematical function. We would have had to take like the derivative twice. And then also, n is 4, it's definitely not infinity. And then, Adam talked about, the bootstrap, about how the bootstrap, like if you use 20 samples, maybe it still sort of works, but 4 is kind of like stretching it a little bit, right? So we're like, okay, so we're not going to use that theory. And instead, well, we're going to use the bootstrap method, even if I just told you that n was not very large either, right? But we're going to use a bootstrap method that is called the jackknife. So once again, someone asked, what is the bootstrap? Why is it called the jackknife? I'm not entirely sure. But so the jackknife is basically a method where you leave one out. So you use n data points to get your estimate. You're going to use n minus 1 or n minus 2 to recalculate your estimate. But so we decided to use n minus 1 jackknife methods. So out of 4, we could find 3 other rearrangements of these 4 elements, 4 rearrangements of these 3 elements to recalculate the estimates. So we actually recalculated the estimates not 125 million times, but 3 times that at every point. All right. So now instead of obtaining one estimate, we use the main estimate with 4 data points, and then we get 4 other estimates with 3 data points, and we can calculate the variance of that. So once we calculate the variance of that, further statistical theory is telling us that when you form the quantity as a difference between your estimate and the truth, and you divide it by the estimated variance with the bootstrap, divided by the square root of the n new number of points, then it is distributed like a t statistic, like a t function. So you can build 95 confidence interval, similar to the one that we showed earlier, where you're going to use the values of the cumulative distribution function for the student's t function, and you can build your confidence interval over your estimate in this way. And it turns out that, that cumulative distribution function value, that t value, is 3.1824. So it's not like 196 as an example, or 2 that you would get from a normal PDF. Okay? So Here's a second example that I will show you today of how we derive concretely uncertainty estimates for the estimates of position and latitude for this data product. Okay? So, I'm not a statistician. I try to be an oceanographer, but I love to talk to statisticians. And so, one of my most fruitful collaborations was actually talking to statisticians as an oceanographer. So, I think it's a good thing to do. All right, so a little bit of validation also of the uncertainty estimates. So what we were able to do, we could actually look at, so once again, I told you that we know what the errors are, right? Because we have the difference between GPS and Argo, right? So this is what is on the x-axis, right? So you know what the errors are. You can actually estimate the variance of that errors, and you can compare it to the error variance estimates, right? So once again, for this paper, so this WMLE method, weighted maximum likelihood method, we actually tested it against other methods of interpolation, right? We used the method called kriging. We also use a simple linear interpolation on the sphere. And then we use the maximum likelihood estimation method, assuming that the errors were normally distributed. And finally, the Poisson methods, where we estimated that where we closely say that the errors were distributed like t-location PDF scale, t-location scale here. And we can compare that to the actual variance of the errors, because we have the error. And so bottom line, this 2D histogram between observed and estimated uncertainty for the two maximum likelihood methods are actually the linear methods, basically, when we say that the position is a function of time, right, are aligned with this 1-1 line. And so most of the time, we find that we do a good job at estimating the uncertainty. And in the paper, we argue that we do a little bit better with the t-location scale that we do with the normal distribution for the errors. However, we still found that we were slightly doing an underestimate of the uncertainties. But it's a caveat of the methods, and we try to be clear in the paper about it. We give you an uncertainty estimate. However, validating it, we found that we were doing a slightly underestimate of it, meaning that this cloud of data is actually, this 2D histogram is actually a little bit below the 1-1 line. So, we stopped there, but we could have tried to improve the model, maybe by increasing the order of the polynomial, maybe that would have made a difference. We didn't quite try that. But we were clear about how our uncertainties were one way of deriving them. They were maybe not the best. And actually, we sort of have the proof that they were not the best. So we wanted, the reader, the careful reader, to pay attention to that. All right, we're over time. But there's one last example that I wanted to show you. And it's relevant to the afternoon activity. So I'm going to take a little bit of, maybe 10 minutes, try to do 10 minutes. Talk about another example of deriving uncertainty estimates. Once again, for the Global Vista program. So that took place in 2022. I grew up a little bit from 2016, and I've had many more meetings and conversations with Adam and others. And so I think we evolved a little bit in our methods, or I did. So the goal in that paper was to produce time series of drifter sea surface temperature estimates with uncertainty estimates, once again, at regular hourly intervals. So all the drifters have a temperature sensor, which is located 18 centimeters below the waterline of the buoy. So it's taking water temperature at the depth, and typically it is thought as SST. But someone else who studies SST might think differently, right? Because we heard yesterday from Naomi about how skin SSTs, sub-skin SST might be different. But here, really, if you talk to someone who deals with SST or ocean temperature, it's going to tell you this is the water temperature at 18 centimeters. However, it's thought about as being SST. So let's just go with that. All right, so the time series of SST, right? So forget about the position. We don't care anymore about the position. But you can look at SST from a drifter as a function of time, right? So this is one drifter trajectory in the Caribbean, North Atlantic. And this is a typical time series. And you can see a lot of very big outliers, right? So we have to find a way of dealing with this. Outliers are a problem because they increase your uncertainty estimate, or it increase the inaccuracy of your data. The other thing is that the sampling is very uneven, right? This is a time series as a function of time of the time interval between consecutive SST measurements, right? So this drifter, as an example, sampled SST every second, averaged every 15 samples, and then transmitted every 90 seconds. And it was tracked by Argos, right? So, and each different manufacturer is going to come up with a different sampling, pattern, right? So it's all going to be very different. And so you can see here those patterns in the sampling interval as a function of time related to the orbital parameters, actually, of the Argos constellation. So it's very uneven. So that's problematic as well. The other thing of importance here is that the SST sensor on a drifter is it's converting engineering unit measurements, into an SST using an SST equation that takes this form, where A is the resolution of your sensor, B is an intercept that is provided by the manufacturer, A and B are both provided by the manufacturer, and N is a binary count, which, as an example, is going to be coded over 10 bits, right? So if you plug this into this equation, you're going to find that the range of observable values by your sensor is between, in this case, given by this equation, is between -5 and 46.15, right? So all the observations from my SST drifters are going to be limited to this range. That's one thing about the way the SST is measured by the drifter. But moreover, the resolution causes a quantization of the data. So you can see, if you zoom in onto a time series, you can see that individual values at the minimum are separated by 0.05 Celsius or Kelvin, right? So that is, we know this is not what's happening in the ocean. This is due to the numerization, discretization of the data, and this is what is called typically in signal processing literature as quantization error. And that's going to happen all the time in any type of observations that you're going to use in oceanography. It always happens. Like in the case of drifters, when we're trying to figure out a few things, we're like, well, this is important. We're going to have to take into account when we're going to derive our uncertainty estimates, or when we are going to take into account our estimation methods, perhaps. Okay? So this is quantization error, and this is something that we had to take into account. So as an example, there was already a data product. So the Global Drifter Program releases 2 products, one every 6 hours, and I have no involvement in it. And then an hourly product, which I have derived with my colleagues. And so if you look at the raw data, right, what I showed you before for one example, these are the black points. And then the 6 hourly creek estimates that are obtained at 0, 6, 12, and 18 of every day, which is akin to an optimal interpolation method that assumes something about the decoration length scale of the data, is providing the estimate value given by the circle, and I have arbitrarily linked them by straight lines, right? But it's really just a circle. And the shading, hopefully you can see, is the uncertainty. So when you look at this, we thought that we could do a lot better. We could really improve on this product by providing an hourly product that maybe was going to capture those things that look like diurnal oscillation of the SST and really is not captured by that 6-hour model, 6-hour method. Okay, so what we decided to do is we started with a model, and I'm convinced now that this is how you need to start. This is how you need to properly derive your uncertainties or your estimates. So we started for a model, a process model, or rather a model of the observation that is telling us that S, observation at stands I, is given by this mathematical function that we are going to define, plus a noise component, right? Model plus noise, physical model plus noise that we're also going to perhaps model. And so the noise component, var epsilon, is expected to be 0 mean, to have unit variance, and locally it is scaled by this sigma k, where sigma squared is the error variance of the observation around time t. So I'm going to say that again. So we're going to say the interpolation time, the time we're interested is tk. And then we're going to assume that all the observations in a window around tk, given by the ti, follow this process model. Okay? So the protocol that we decided to use is shown here. We have two components to it. The first term is a polynomial of order p, and the second component is a sum of cosine functions with an amplitude and a phase. Right? So the reason why we devise such a model is because we know that you have diurnal oscillation in SST. Okay? So we wanted to model that periodic change, that high frequency periodic change by a sum of cosine functions. So you can actually reorganize this, right, by expanding the cosine, and you can write it as a sum of a cosine and sine function with two different amplitudes in front. Okay? So we have a low frequency component modeled by a polynomial, and we have a diurnal evolution modeled by a sum of n sinusoid and cosine functions. As an example, Charles Gentleman came up, with some very similar models. All right. So we took that model, and if you look at this model, we are going to try to fit the parameters for it, and then we're going to evaluate it at time ti equals tk, which is the evaluation time. But when you do this, the expression reduces to this, where you have two components. One component, which is the order 0 term of the polynomial, and another component, which is only the alpha coefficients in front of your cosine function, right? So you have a parameter, you have a model with p plus 1 plus 2n parameters, and then at the end, your estimate of SST is basically n plus the sum of n plus 1 term. Okay, so how does it work? As an example, this is real data, and we want to estimate the SST at time tk here. So if we use a model of, so we have a bandwidth, once again, we're going to have a sliding bandwidth, but this time, for this estimate, we're going to use to be constant in time. So the bandwidth we're going to take is actually 1 day. 1 day forward and 1 day backward with different weights. Okay? So what we did is that if we assume that your model, we have a choice, right? If we assume that the model is polynomial of order 1 and no sinusoid at all, then let's say that's equivalent to the model that we use for position and velocity. It's just a polynomial of order 1. So if you were to fit a line to the data, it would probably looks like this. And then you evaluate it at time tk. And so your estimate is right here. That's that red dot, right? The data was actually here, and the estimate is here. So we can do a little bit better with this. So we go to the next model, where this one we're going to keep p equals 1, but then we're going to allow for 3 sinusoids in the model. So now we fit those 4 parameters, right? And actually, because we have the cosine and the sine, it's more like 8 parameters. And then now the complete estimate by the total model is given by the blue curve in that window, but the estimate at the time tk is given here. And then the components that comes from the background polynomial is given here. The total SST is here. The component from the background polynomial low frequency is here. And the difference between the two is the diagonal component. So then you do that at time tk, and then you move forward, you move the sliding window, you choose another time tk, and you keep going like this. So as a function of time, different tks, you obtain your subsequent estimate here, here, and here.